Hello, we're going to be talking about hashing algorithms in this video. And in the next one, we'll look at some examples of how hashing is used. This one is purely just what they are. So a hash algorithm is an algorithm that scrambles data in a way that cannot easily be reversed. So this algorithm is often called a hash function. It's some code which is able to take an input, like a normal string or a normal number, and scramble it to a completely random looking output. And the whole point is it can't be easily reversed. I can't then take this output and work backwards to give me the input. The output from a hash function's got a few different names: digest, hash value, hashes, hash sum. It's got a few different names, but it's just the output from a hash function. Now, I've left a weird gap in this input because the input can just be one item, but sometimes we also have a second input along with our original data. And this is sometimes called a salt. So a salt is a random value that may also be input alongside your normal input. And the aim of this is to reduce predictability. And we'll look at why you may use a salt in the next video. The whole point is, if I apply the salt, I get a different output to if I didn't have the salt. So adding the salt gives me a whole different output, which helps with reducing predictability. Now, I said this in the definition at the top that it cannot be easily reversed, but really a hash function needs to be or should be a one-way function. That means there is no way to work backwards from the output back to the input. That's the key difference between hashing and encryption. Both involve scrambling data, both use mathematical techniques which are loosely similar. The key difference is encryption, you can reverse it if you have the key. If you can't have the key, it's not really reversible, ideally. If you have the key, it can be reversed. Hashing, there is no key, there is no way to reverse it. And this is the most important property of a hashing algorithm. And it can be hard to understand why we would even use hashing. We'll leave that till the next video, but there are uses for this, I promise. Now, like I said, that's our biggest characteristic we need. It needs to be a one-way function. However, depending on what you are trying to achieve, there are other potential desirable properties of hashing algorithms, because like encryption, there are loads of different algorithms which have got pros and cons and have got different properties. So a fairly obvious desirable property is it's fast to execute. Another property we often want is a variable length input being mapped to a fixed length output. Well, what does that mean? Well, a variable length input means the input can be any length. It can be really short, it can be quite long. There will be a maximum limit often, but that can be quite a big limit actually. So any size input is converted, is mapped to a fixed length output. The output is always 25 characters, 200 characters, or 300 binary digits. There is some fixed length, and no matter the input is mapped to that output. And this can be useful because it can obscure further what the input was originally. If a 5-letter input was always mapped to a 5-letter output, and you knew that, well, that reduces the number of possibilities the input could have been, so that might make it easier to break. But in this case, a 5-letter input might map to a 20-letter output, and a 7-letter input might also map to a 20-letter output, which makes it harder to try and reverse. And another property, which is more of a key term, is we want hash functions to be collision resistant. Now, a collision is when we have two different inputs which map to the same output. Input A and input B are different here, but in this rubbish algorithm, they've both ended up being this hash value. That is a collision, and we want our algorithm to be resistant to this. We may sometimes have collisions in some cases, but we don't want it to have many collisions, and in some cases we want there to be no collisions. Another important property, which has a key term, is we want hashing a lot of the time to be deterministic. This means that no matter which computer I run the hashing algorithm on, no matter what time of day or program I'm using, it should always produce the same result. So it should be very consistent across different users and at different times. In other words, input A will always give you this output no matter what. Another common property is we want hashing to exhibit the avalanche effect. Now, an avalanche, I'm sure you know what an avalanche is, starts with a tiny movement of snow. A tiny change results in cumulatively a massive effect where it grows and grows and grows, and suddenly you've got half the mountain descending. So in terms of hashing, how does that relate to hashing? Well, a tiny change in the input should result in a massive change in the output. So a tiny change has a huge effect on the output. Now, to give you an example of some of these properties being used in actual real hashing algorithms. Let me show you kind of the latest best one as of right now, which is called SHA-3. There was a SHA-1 and a SHA-2, which have been replaced with SHA-3. Now, we don't need to know this by name or know how it works, but just for your context, it uses lots of maths, but it will use things you recognize, like bitwise XOR. That's often used in hashing algorithms in various different ways. The whole point behind the maths behind it is we want it to become scrambled, but not reversible. And interestingly, there have been no collisions found in SHA-3 so far. So some of the best hashing algorithms don't have any collisions as far as we know. To show you an example of how this looks, well, I've put test in as my input. I've not used a salt in this example. And SHA-3 produced this as a scrambled up output. And there is no way of reversing it. So I can't take this output and find the input. If you manage to figure out a way to do that, you'll become really famous because nobody's done that so far. And to show you the avalanche effect, if I was to make a tiny change in the input, I've added an exclamation mark. That's a very small change. However, the output is completely different. Massively changed the output. It doesn't resemble the original one at all because of this tiny change. And this is good potentially because it reduces predictability. It means I can't see any patterns because it's just all random seeming. And SHA-3 should be deterministic. You should be able to Google SHA-3 online converter. I use the smallest possible output, which is 224 bits. If you use that version, you should be able to replicate what I've just done here and see the exact same output. This output here should only work test with a capital T because there are no collisions found so far and because it is deterministic. So these are all the key properties we need to be aware of for hashing. I've not really said what hashing is used for, so we'll look at that in the next video.